shear and bending. So you can cut a beam and find the internal V, the internal, the axial, and the internal bending moment at the cut. But we're interested in the variation of that shear and bending over the entire beam. You know why we're interested in those? So when you get to mechanics materials, and you're choosing a beam size and shape and a material, the distribution or the variation of shear or bending moment over the entire beam, what you're looking for is the maximum bending moment, and you're looking for the maximum shear. And so by graphing it, you find where the maximum is and where the minimum is. And so that's important. That's what we're looking for. That's why we do it. When we get to equations, if you look at equations, people don't. If you're not in mechanics materials, you don't appreciate this. So when you get to equations, you go, why in the world do we write the equations anyway? The graphical method will get me the thing. Why the equations? Well, when you get to mechanics materials, when you get to beam loading, one of the things you're interested in is the deflection of that beam. And you're going to calculate the stresses in that beam in a particular place. But you're interested in the deflection of the beam over its length. And there's two ways to get beam deflection. One is called superposition, where you basically kind of use standard beam formulas of concentrated loads and uniform loads and triangular loads, and you add those guys up to replicate the loading on your particular beam. The other way to get beam deflection is to integrate. And so if you have a load function on a beam, this is just a simple case of a point load. But what if this is a distributed load, or different sections with different loads? So if you take a load function and integrate that, you get shear. And if you take shear and you integrate that, you get bending moment. And that's where we stop in statics. But in mechanics materials, you'll integrate the moment equation to get the slope of the beam. And then you take the slope function and integrate that, and you get deflection of the beam. And so a single point load in the center of a simply supported beam, the deflection curve looks like this. And you can actually get that deflection curve by integrating 1, 2, 3, 4 times. Okay? And again, in statics, we're just going to write equations for shear and bending moment. But in mechanics materials, you're going to take those two more directions. Now you have to multiply your equation times some other constants. But that's why we want to get the equations. Okay? Trust me, you need these guys. So that's why we're doing it. That's why we're interested in it. So when I talk about bending, producing bending moment diagrams, shear and bending moment diagrams, to me there's 3 rules. One rule is a point load. There's variations of the rules. So the first rule has an A and a B. So the A part of this rule basically says if I have just point loads on a beam with point supports, these point loads produce jumps in the shear. And so if I just have 3 support, and point load, my shear curve jumps when there's a support and falls when there's a 10, and there's nothing in between. So we jump up 5, constant, jump down 10, constant, jump up 20, come constant, jump down 30, and then back up 15 to 0. So just point loads produce what's called basically a square wave. And then the bending moment, so if you look at our slope relations, which we're going to get to down there, and you guys should be able to write these from memory. So we basically have the slope of the shear at a point is equal to the value of the load. If we separate variables and integrate this guy, we get the change in V is equal to the negative of the integral W dx. And then we have the change in the moment, or so the dm over dx is equal to v. And the separated variables integrate, the change in moment is equal to the integral of v dx. And so these are slope and area relationships that we need to know. And so if you actually look, this is a super simple case. But my load is 0. There's not a distributed load here, so my load is 0 here. So if my load is 0, then the slope of my shear is 0 in that interval, which is right here. When I go down to the moment curve, the change in my moment, the delta m, is the area under my shear. And so the area under shear is a positive 10. So my bending moment is going to start at 0 and go to 10. And the slope of the dm over dx is at a point is equal to v. Well, v has a constant value of 5 over this entire interval. And so m has a constant slope of 5 from there to there. Okay? But the main rule is really the point loads produce the jumps in the shear. But this also illustrates these guys. Okay? Couples, on the other hand, correspond to jumps in the moment diagram. And so in an extreme, this is an extreme example. So this is an extreme example of a beam that only has couples on it. And so it's got a couple, this is a couple here and a couple here that are basically supports. And then you've got a clockwise couple, a counterclockwise couple, and a counterclockwise couple. And so this beam that has only couples on it, there's no shear at all, but you've got a moment curve that corresponds, that jumps at these couples. And so, which leads to my couple rules, which are here. And so there's two different couple rules. Let's pull this down. Are we still? Sorry. Hello? 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 There we go. Okay, sorry.
He's a little shy sometimes.
Yeah. So which gets to these couple rules. And there's a rule for the interior of the beam, which is what your crib sheet gave you. But there's a separate rule for the ends of beams. So if you have a couple at the end of a beam, like a 10 here, then my moment here is going to start at a positive 10. Remember, a positive coupler produces upward curvature in this segment. So upward curvature is positive. And so that's a positive 10 at this end. But at the far end, at this support, I've got a 20 Newton meter couple downward at the end. And so that downward couple produces downward curvature. And so this guy ends at a minus 20. And so this rule here gives you the starting and ending point of your bending moment curve. And so before you ever start writing a bending moment curve, you look at this beam and say, does it have a couple at the left end or a couple at the right? And if it does, then you know it's not going to start at 0 and end at 0. It's going to start and end at a couple at the end. And that follows this rule right here, okay? And then internal to the beam is a slightly different rule, and that's the rule that's on your crib sheet. So that's the rule that's here on your crib sheet, and this is the rule for interior couples in the middle of a beam. And that interior couple, so a clockwise couple produces a positive jump, a counterclockwise couple produces a downward jump. And counterclockwise is an additional downward jump, okay? And so, you ask, well, why do these produce a jump? And so basically, so remember, drawing a free body diagram of this beam is ground truth. If you're ever curious what's really happening, just cut it. And so if we cut this beam right here, just somewhere in this first interval, you basically have 10. And then you have, so that basically to keep this guy in equilibrium, you have a bending moment that acts this way that's equal to 10. Anywhere in that interval, a positive 10. And so and that's what the graph shows me. Once I cross that 5 Newton meter and I cut a free body diagram in this second section, and I look in that section, I've got 10, I've got 5, this is my bending moment at that arbitrary cut. And 10 plus 5, and so that's moment 15, which is what my graph shows me. And so if you're ever wondering, is that really the value in the middle of that interval? Draw for a cut, draw for about a diagram and calculate it, okay? And so these rules are constructed to give you the same result without having to draw the free body diagram or write any equations, which is good. But you have to learn the rules. So those are a couple of rules. And then finally, the slope and area relationships, which I just showed you, these guys, and which we'll illustrate here in a moment. Questions on that? So those are our rules. Let's work a series of examples. We'll start simple and work our way to a little bit more complicated. What are we doing on time? 7:44. So this is a really simple example with just point loads and supports. And we basically already worked this example. And the AY is 114.3, the BY is 885.7. And so you end up with a square wave on your shear, and then the bending moment is just up and down. This is a positive area, a negative area, positive area. And my moment curve starts at 0 and closes at 0 because there's no couple here and there's no couple here. Okay, so simple case. Here's another example. So this is a uniform load here with a point load, and now we have a couple out here. So I have an 8 kilonewton meter couple here. Good news, on your exam, they typically will give you the support reactions. And so just pay attention to the exam and they'll give you the support reactions. And the way the problems work, let me just show you a problem. So the way shear and bending works on the exam is they typically will give you a load curve, and then you have to find the shear curve. And they ask you some questions about the shear curve. And then there's another problem, which will be typically is different, where they give you a load curve, and they give you the shear, and then based on this guy, they ask questions about the bending moment. And the reason they do that is if you get messed up on the first, and then you're really going to get messed up on the second, and so they're two typically different problems. Is how it works. And so they'll ask you, well, does this jump here? What's the change over this interval? And we'll get back to this in a moment, but that's how it works. But back to this question. So the support reactions will be given to you. So AY is 20. BY is 32. And so the shear diagram is we jump up 20 from the AY, it's constant. We jump down 12, which takes us to 8, which is constant. We come to the distributed load. And the total area under this distributed load is 10 times 4, which is 40. And so remember our the change in our shear is the negative of the area under our load. So the under our load is 40. And so over the interval, we're going from positive 8 to a negative 32. That's the total change. And then we're going to jump up 32 back to 0 here. And so that's the curve. We actually need this crossing point, okay, because we need these areas. To get this crossing point, there's a couple different ways to do that. One way, so so this is x, and this is 4, and so this is x, and this is 4 minus x. How do we get x? And so you can basically draw that picture. And so this is 8, this is x, this is 4 minus x, and this is minus 32. And you can basically say, or basically just call it 32. And these are similar triangles. So similar triangles. You can basically say that 8 over x is equal to 32 over 4 minus x. One of the easiest ways to get that, because those triangles are similar to one another. And then you can basically just solve for x. So you go 8 times 4 minus x is equal to 32x. And then that's 32 minus 8x is equal to 32x. And then you got 40x is equal to 32. And x is equal to 32 over 40, which is 4/5, which is 0.8. Okay? So that's one way to get x. And if you have a uniform load, you often need to get x. Another way to get x is that basically the slope of this guy, which is delta y over delta x, is equal to the value of w, which is 10. Okay? And so this delta y over x is 10, which is equal to 8 over x. 8? Yeah. Which is equal to 8 over x. So you basically have 8 over x, 8 over x is equal to 10, delta y over delta x. And so from that, you get x is equal to 8 over 10, which is 0.8. So there's two different ways to get x, but choose a way that works for you. Okay? So once you get x, we need all of these areas. This is funny. Getting used to the gimbal. So he's back. So if you guys happen to notice that it's not following anymore, you might call my attention to it or whatever. It's like teaching a classroom full of students. They all just phase out and don't follow you at some point. I mean, students just give up. So the gimbal does the same thing. It's like, I thought we had a smarter gimbal than that. So we're finding the areas under these curves. And so 20 times 2 is 40. 2 times 8, which is 16. This is 8, and this is 0.8. So 1/2 of 8 times 0.8 is 3.2. And then the area under this guy is, so 4 minus x is 3.2, and this is 32. So 1/2 of 3.2 times 32 is negative 51.2. And so when we go down to the moment curve, remember I've got a couple here. I've got a negative 8 here. And so my moment curve is going to start at negative 8. And there's no couple at this end, so you know you're going to close at 0. So you know the two endpoints. And so starting at the negative 8, I'm going to go up 40 to 32. And then I'm going to go from 32 up to 48. And then I'm going to go up another 3.2, which takes me to 51.2. And then I have negative 51.2, which takes me back to 0. So those give me my points as I go. And what are the slopes? So the slopes, remember that the slope of my moment is equal to the value of v. So v is 20. So I have a constant slope here. My v here is 8, and so I have a constant slope 8. This is a linear curve, so now I have a parabola of the second order. And so I have a curvature to this guy, which takes me back down to the 0. And so remember in shear and bending, if you've got a linear load here, or a constant load, then you have a linear function here, and then you have a parabola. If we have a triangle here, then that becomes a parabola, second order, and that becomes a cubic here, which is third order. Okay, so you remember that from your homework. Questions on that? So that's a uniform load. It's a uniform load. Let's talk about another problem, which is a triangular load. So this is a triangular, an ascending triangular load at a uniform load. 6 meters long. So you who just came in, these handouts I'm going through are actually on the OneDrive. And so if you know Josh, you know Josh. Okay, so Josh will send you the link to the...
That's Josh's surveying TA.
Yeah. Okay, so you're the smart guy that everybody keeps talking about.
Apparently.
Okay.
Look at his face all red.
So this is an ascending triangular load here. We find the support reaction, so AY is 10 and BY is 17. And so graphically speaking, the area under this triangle is 1/2, so this is 6. So it's 1/2 of 3 times 6. So 1/2 of 18 is 9, is the area under this guy. And the area under this guy is 6 times 3, which is 18. And so when I come down to my shear curve, I'm going to jump up 10. And then I have a change in 9, so I go from 10 down to 1. And then from 1, I'm going to go from 1 down to negative 17. And this is a triangle, so this is second order, so this is parabolic. And then this is a straight line, this is constant, uniform 6, and so this is a slope of negative 6. And then I jump up 17 to go back up to 0. So this is my shear curve. And then my moment curve is the area under this guy, which actually gets kind of complicated. Because this shape here consists of 2 pieces. There's like a 3 by 1, and then you've got this parabola here. Because the slope of this V is equal to the value of this W. The value of W is 0 here, so the slope here is 0. So remember your area functions for a parabola. That's working, good. So if you have a parabola, if this is a tangent point right here, tangent, with a 0 slope, and this is B, and this is H. This has to be tangent, but if it is, this area here is 2/3 of base times height, and this area here is 1/3 of base times height. In this particular parabola right here, because the slope of this guy is equal to the value of W, this is a 0 slope. And so I can use and I know this is 1. And so I know this is 10 minus 1, which is 9, and then this is 3. And so the area under the parabola is 2/3 of 9 times 3. And then plus this 1 times 3, which is 3. And so the total area here is 21, okay? And so in this case, we could use that formula. And then you could find the areas here, which I did, the same procedure I showed you before, to get the peak